Now, from our assumption here, G alpha is in tau sub 1 intersection tau sub 2. This means here that G alpha is in tau sub 1 and G alpha is in tau sub 2. Being G alpha in the intersection, in tau sub 1 intersection tau sub 2. Since tau sub 1 is a topology, it means therefore here that the countable intersection of G alpha is in tau sub 1. Again, since tau sub 2 is also a topology, we can say that the countable union of G alpha for all alpha is in tau sub 2. Now in this case, as you can see, the countable union of G alpha is in tau 1 and the countable union of G alpha is in tau 2. Hence, we can say that the countable union of G alpha for all alpha is in the intersection tau 1 intersection tau 2. So we have shown this one. Hence, we can say that condition 2 is satisfied. Third one is we will show its finite intersection. So for our third, we will let G and H be in tau 1 intersection tau sub 2. We will show the intersection of G and H, which is in tau 1 intersection tau sub 2. Now in this case, because we have here our assumption G and H are in the intersection, this means that G is in tau 1, G and H rather, G and H are in tau 1 and G and H are in tau 2, right? By using the definition of intersection. Then again, since tau 1 is a topology, so we can say that G intersection H is in tau 1. Also, tau 2 is a topology, we can say that G intersection H is in tau sub 2. So, since G intersection H is in tau 1 and tau 2, we can say that G intersection H is in the intersection of two topologies. So as simple as that. And the third condition is satisfied here. So we can say that the intersection of two topologies is a topology. So we're done proving the first statement. Actually, this statement can be generalized to any collection of topologies, as stated in this theorem here. So, we let this tau sub I, where I is in big I, be any collection of topologies on a set X. Then, of course, the intersection, we have here the finite intersection of topologies is also a topology on X. Now, let's try to answer our second question. What about the union of two topologies? To answer this one, we will show an example. So we let X be this set. We let X be equal to A, B, C. And then we will consider two topologies here. Say for example, tell 1 be equal to empty x and then a. Actually, this is a topology. Why? Because empty and x are in tau 1. And then if you are going to get the union, still it is in the collection. And also, if you are going to get the intersection, still it is in the collection tau 1. And then we let tau 2 be equal to empty x and then the set C. Okay. Now, we will get the intersection of this. The intersection of this is, the union of this is tau 1 union tau 2 is equal to empty x and then this one. So this is the union of two topologies. Now, we are going to show if this is a topology. Okay, the first condition, we have empty and x are in the collection. Now, what about in the second condition? So, countable union. Now, if we are going to get the union of this one, it is AC. We have A, set A, union set C is the set AC. So, take note that the set with elements AC is not in the collection, tau 1 union tau 2. So, this is not in the collection. Hence, this violates condition number 2. That is, condition number 2 is not satisfied here. Therefore, we can say that tau 1 union tau 2 is not a topology. Okay. So, note here that the statement, the union of two topologies is a topology is not true. Thus, that is equivalent when we say that we disprove the statement that the union of two topologies is a topology. So, by the way, to disprove a statement, sometimes it is enough to show an example, just like in our statement, the union of two topologies is a topology. So, we have shown that an example that it is not a topology, therefore, that statement is not true. Therefore, the union of two topologies is not a topology.